All right, are we live? Okay. Oh, no, this is. No questions, no nothing. All right. Since there is no uh, questions, actually, hang on, let me just close the window. Old house, lots of squeaky things. All right, so since there was no questions about what we did last time, let's do some new things. All right, so we're going to start with. Let's just see. Does it look okay? 1, 2, 3. Let's talk about frequency distributions. And to do that, we need to start looking at data. And the thing about data, the thing about data is that it always comes with R2D2. The thing about data. So we ought to start with some basic definitions. Well, data is one of them, and that is any observation that you have collected. So you can summarize it, you can analyze it, you can interpret, you can make decisions on it. So data is the heart of statistics as such, because it gives us access to something we actually can do something with, and what we can do with it we will talk about in a second. So this is any observation. That has been collected. So that's that. So what do we do with it? Well, we can do statistics. And what do we mean by statistics? We mean, the obvious things like collecting. Collecting data is statistics. Analyzing data is statistics. Summarizing data is statistics. Then we can also interpret data, right? We can draw conclusions from data. So, and then there's etc. etc. So there, statistics is this way we look at numbers. And again, in mathematics that you took so far, some pre-calc or algebra classes, you looked at numbers in a very linear fashion. There's one number, there's some formula, there's another number afterwards, and this chain kind of repeated. This x formula for, say, a line, and this y, x, something, y, In statistics, it looks very different. You have a huge dump of information, and out of this information you sift it out and go, and here's the pattern, or this is what we can do about it, or this is what we can say about it, or this is what we would like to say about it, but the question is, do we have enough data to be able to comfortably talk about it? Which Sounds great. Well, we gotta start somewhere. Population seems like a good place to start, and population is a complete set of data. So a complete set of elements, a complete set of items. Population of the United States, regardless of which way you look at it, it's everybody inside of the United States, right? Or you can define it as everybody with American passport, or you could define it as everybody within the border, or you could define it as everybody that has been here for at least 15 generations. Pick and choose your definition, but once you have the definition, you can collectively name a set that contains all those things, right? For example, all people taking PUBA 341 section 4. Ta-dam. And there's everybody on your attendance list. That's your population. So what is a sample? Well, a sample is some subset. Some subset of what? Well, of population, right? Of this. Some subset of this. Now, why would we want to deal with a subset? Well, because it is smaller, right? Here's the population of black pens. Right, let's get rid of this. Do you really want to check if all of them work? Or do you want to take like 3 of them, check those 3 and be like, oh, okay, those pens work. Right? That's kind of the idea, is to take a little bit versus a lot. Because here's the problem. Census. So the census is collecting data from every member of a population. Well, somebody said that they like my stone metaphor, so let me pick up my set of stones. Alright, so here's the exciting point. Here's the population of stones. It's relatively large, right? Okay, but it's not big enough. Let's make it bigger. So here's the population of stones. I know how many white stones there are, but there's population of black stones. Okay, and suddenly we have this population of stones There's your population, black and white. And I'm not trying to make a metaphor for political reasons. This is just an observation. So I have this population. And so my question could be, how many black stones are there? Well, you could count all the stones, right? And count how many of them are black, how many of them are white, right? And figure out how many black stones there are. Again, this shouldn't take too long. There's maybe 250 stones on the table. Easy to do. Maybe a little bit less. It should be easy to do. Well, 1, 2, 3, 4, right, 5, and so on and so forth. But what we could do is we could say, hey, out of all those stones, I'm going to take a sample. There's my sample. Okay, get rid of all the other things. Right? And here's my sample. And my sample says, well, there's 3, 6, 9, 12, 15, 18, 20 white stones and 8 black stones. So you know, this. So the proportion of stones in this thing is 8 out of 28, right? 8 out of 28. Now, if I count those things, will that make sense? Maybe. But this is way faster than doing all this, right? All right. So this brings us to the problem with census. What's the problem with census? Have you ever heard the term census? Well, assuming that you've been around social media in the past year, you heard that term census because, the US census of 2020 is about to go. And what does it mean? It means we have to check how many people live inside of the country. And how do we do that? Well, we go door to door to door to door to check. Right? We could maybe run some set of statistics, but we are just going to go to door to door to door. It means we have to hire 50,000 more people and pay them millions of dollars, and yes, we're going to get a relative good collection of data and figuring out. Just that's a lot of people. The United States has 320 million, 325 million. That's a lot of surveys. That's a lot of things. So we would much rather, if we could, take a sample. Take some random measurements, and just like we did, with this very fancy tool called the main sampler, right? Take a little slice of it and take a look at what's going on. And we do have good enough statistical models to get some information that might be useful. Now here's the problem. Even if you look at this setup right now, if I take a sample right here, right on top, that sample is going to be very white. If I take a sample right here, right, that sample is going to be very black, right? And so we run into a problem where there could be issues. So, right, samples need, and I will underline need, and we're going to see this statement a lot, but samples need to be random, because otherwise they don't make sense. Alright, so this is part one of the conversation. So let's expand. Actually, I should probably get rid of those stones. They're just somewhat in the way. You know what? I'm just making a lot of noise. Hopefully you don't listen to my stream with a pair of headphones, but all cleared up to be used in the future. So this is the basics. So now let's take a look at it. While this whole it needs to be random part sinks in, while this is important, let's take a look at the types of data we might be interested in. So types of data. Well, first of all, naming. If we are talking about a parameter, we're talking about a characteristic of what? Well, of a population, right? PP, kind of easy to remember. So when I say, hey, this set of data has this parameter, means I ran a census because I have a characteristics for a population, which means everybody. On the other hand, if I say, hey, I have this statistic, I mean a characteristics of a sample. So people say, hey, the statistics for the sample is 7. Well, you'll know right away that we are talking about a sample and some calculations that we did on that data. All right, so that's one way to look at it. Well, what else can we look at? Well, we could look at qualitative or quantitative. Qualitative data, also sometimes referred to as categorical, I think it's spelled, and this one is usually referred to as numerical. So qualitative data is things that usually are not numbers the way we understand numbers. Color is a qualitative piece of data. Is the stone black or white, right? Is it just white, or is it white with little lines on it, right? Is my favorite color red, for example, right? What's gender you have, race, religion, right? Those are things which definitely don't have numbers. And then we run into couple things that are more interesting. So say color, gender, religion, but zip code. Zip code is a number, but it doesn't behave like the numbers we usually encounter. You cannot add to zip code and get a third zip code that actually makes sense, right? Hawaii minus Washington DC doesn't give you Oakland, right? That doesn't make sense. So zip codes, phone numbers, right? ID numbers, they don't make sense. Why? Because you cannot do math on those things that turns out any meaningful results. I mean, you can keep on adding the numbers, just there's no meaning behind it. Where in case of quantitative data, we're talking about numbers which do make sense. Wages, weight, height, right? Miles per hour, what else? Time, right? And so on and so forth. Those things as numbers make sense. We can do something about it, right? We can look at the wages of one person, the other, subtract the smaller from the bigger, and get the difference in money, right? So there's a lot we can do number-wise. There's not much here that we can do calculation-wise, right? So that is great. Well, quantitative data has also a somewhat cool feature. So if we just look at quantitative data, it has an interesting feature to it. One is that we can have it discrete. Discrete data means it's countable, finite. So quantitative and finite data is data which you can count. Number of eggs, right? Number of dice, number of stones in a bowl, right? this is something that if you had enough fingers, you can actually add up and have an answer, right? Eggs would be so. Eggs, dice, pencils. Right? And then we have continuous. Continuous data. And continuous data is much more interesting. Continuous data means the following. Means that given the chance, the number of possibilities or possible values is infinite. What does it mean? Well, look at age, for example. If we're talking about age the way adults talk about age, right? People say, I'm 23, I'm 24, I'm 27, I'm 47, I'm 62. It's a very specific, countable kind of way to look at it. It's a discrete piece of data. But if you look at age the way 3-year-olds talk about age or 5-year-olds talk about age, they are, well, I'm 3 years, 2 months, 1 week, 4 days, 17 hours, right? 22 minutes, 16 seconds. And if you gave them a watch precise enough, they will be like, and 792 1,000th of a second, and so on and so forth. Which means that the actual age becomes a measurement on a very, very long scale, which has very, very many divisions. If you have a hard time wrapping your head around it, let's play a game. And the game goes like this. Pick a number between 10 and 0. Let me just double check if there's no more questions for me. No, it doesn't look like I'm getting. Doesn't look like I'm getting any love. Nope. Nobody wants to talk to me, and that's okay. So let's go back to this. Pick a number between 10 and 0. Whatever number you pick, say you pick 4. Pick a number between 0 and 4. 1. Pick a number 0 and 1. 0.5. 0 and 1. And so on and so forth. And as long as you have enough paper, or you like numbers enough, or you have a good memory, you can play this game forever. And eventually somebody's gonna go, and I can tell you that you can pick another number between this and this. What's the limit on this exercise? Well, this limit on this exercise is based on how good your measurement is, how good your ruler is, how good your memory is, right? So this kind of continuous data is usually a measurement. Right? Which means that the precision, right, of the measurement, the precision of the data comes from how good your ruler is, right? If I look at this ruler, well, I can get down to what? That's 1/2 inch, that's a quarter, that's an eighth, that's a 16th. But then you have a little division, so I can go down to 1/32 of an inch, and I can probably estimate in the middle, so call it 1/64 of an inch on this division alone, right? In this case, this is a centimeter, so I can get down to half a centimeter, 1 millimeter, so I can account for maybe half a millimeter on precision. But this is as precise as I can get. Of course, me being an engineer by training, I can get fancier, right? I can get to 100th of a millimeter in precision, right? Which has its benefits and it has its drawbacks. But again, the measurement is here. And that's important. And we're going to get to that in chapter 3. So just keep that in the back of your mind. And then we get to 4 levels of measurement. Well, if we are talking about data and measurements, let's look at the 4 levels of measurement. This piece of information isn't always applicable in real life the way it's presented to you right now. What is your understanding of what kind of data you can collect and what kind of data you are getting and what you can do with it. Because for qualitative data, we have 2 choices. We have nominal and ordinal. Nominal means just categories. There's no arrangement, there's no order. Say religion, right? Try ranking religion in a, number 1 something, number 2 something. You're going to upset somebody who end up on number 2, or worse, somebody who end up on the 3 on the position, right? So those are categories. They can be arranged. They can't be arranged, right? There is nothing you can do about it. We can arrange the words alphabetically, but that's different. We cannot rank religion. We cannot rank race. We cannot rank gender, right? So this is just categories. Ordinal are categories that can be ordered. Rank is a way to look at ordinal data, right? A captain is higher than a sergeant, a major is higher than a captain, and a general is higher than a major. We cannot do much else with it. We cannot really perform any kind of calculations on it because what is a general minus a captain, right? Or a general minus a sergeant? Well, a general minus a sergeant is a captain that cannot make his own coffee, right? It's kind of absurd way to look at it. Kids in grade school at a race, right? Well, we know which kid came first, which came second, but we really don't count the seconds between them. We just know that this one came first. So the ordinal ones differences are meaningless. And then we get to data that isn't qualitative, data that is quantitative. So we have interval. An interval is data that is ordered or can be ordered, and differences are meaningful, right? So you can do differences. What would be a good example? what could be a good example of this? I suppose to some extent temperature, the way we experience it on the thermometer, right? Temperature in a thermometer. You can have a positive number, you can have a negative number, there's a difference, but that zero, right? Or we call it natural zero. Natural zero does not exist, right? Natural zero means that there is a place with no temperature. Now, if you're looking at it from the physics standpoint, there is theoretically a place called 0 degrees Kelvin, which is the absolute zero where temperature doesn't exist because heat doesn't exist because there is no movement. I'm sorry. So there is a natural zero, just not the way we experience it. Plus, we cannot produce it. Like, we know it's there, we know it should be there, but we just, it's kind of like, it's there. It's like the Twinkie in the back of your couch. You know it's there, but you cannot reach it. So interval data is one that doesn't have a zero as such, right? So you can go up and down and whatnot. In a functional country, GDP doesn't have a zero. Right? You can have a negative GDP, you can have a positive GDP, you can have a zero GDP, but that zero doesn't mean actually no one is producing anything. It just means that the balance, right, is zero, right? I think that's a good example. I'm not very good at economics, so you're gonna have to excuse me on that. All right. So that's interval. What's the last category? Well, the last category will have the order, the differences, the zero, and it's called ratio. And we're looking at data that is ratio, that is data that is ordered, that has different variances, are meaningful, and has a zero. Number of tickets sold has a zero. You can sell 0 tickets. You can sell more, and the difference between more and even more is meaningful. But right, having a ball with stones, right? You could have 1 stone, you could have 5 stones, and the difference between 5 and 1 is 4 stones, and that's meaningful. But you could have just 0 stones, period, right? So ratio is like that. It has that anchor point. Now that anchor point is the difference between interval and ratio. But both of those are considered quantitative pieces of data, and there's a way you can work with it. I would ask you if there's any questions, but I'm talking to myself. It's insanity at the greatest. All right, let's see what we have next. All right, so where do we go from here? Well, from here we can get to a couple places. One of them is we could look at situations in which we get to collect data. And this is a question between an experiment versus an observation. And the difference is relatively straightforward. An observation is just a measurement. So you don't do anything, you just ask questions. Polling is an observation. Taking surveys is an observation. Asking people simple questions is an observation. There is some fine tuning that needs to happen when you do surveys and polling, because there is bias that you can introduce to the question by presenting one question after the other, right? If you present a question about gun violence after you show a picture of Sandy Hook massacre, people are going to have a different reaction than if you don't show it. Now that reaction could be left or right or up and down, but there will be effect of it. So you have to be careful. So there's a whole science on how to build survey questions and polling questions, but we're not going to cover this. Just be aware of it. So observations is we do not modify the subject. We just test and measure specific traits. So we ask specific and hopefully meaningful questions. And then you have an experiment. An experiment is very different. The experiment talks about applying treatment to a subject and then measuring or observing the effects. An easy way to think of it is drug trials, right? You give somebody a pill and then you see if they feel better. Placebo effect comes from that, right? Comes from the fact that I gave you something and you're like, oh, I feel so much better. This is my lucky stone. I will pass, the exam and whatnot. No, that wasn't the lucky stone. This one is the lucky stone. But, you felt like this was. So it affected the way you answer the question. It adjusted the measurement. All right. Well, again, are we willing to go through all these stones as a census? Yeah, no. We will try to avoid doing a census when we can. In some cases, we do want to have a census done because it's worthwhile to know exactly how the population is distributed, how it behaves and whatnot. But in most cases, we will be satisfied with a sample. It's smaller, it's easier to work with. And because it's smaller and easier to work with, it's probably cheaper to get, which is a biggie, right? Surveys cost money. A survey can cost you anywhere from a couple cents per survey to $20-$30 per survey if there's some statistical tools attached to it. Ask 10,000 people and suddenly that amount of money becomes humongous, right? So there is several reasons why you would want to take a sample. Well, so how do we take a sample? Well, we want to take it, right? It said right here, samples need to be random, right? So what's random? Yeah, I know it feels stupid and asking such a simple question, but it's important. Random means the following, means that each member of a population has an equal chance of being selected. Sample. Which means that a random sample from those stones means that every one of those stones has the equal chance of getting selected. Even the ones on the bottom will have an equal chance of being selected. So that's random sample. Well, we could go simple random sample. And I've seen this mentioned in one paper, which says that each group of size n has equal chance of being selected. So the difference between random and simple random sample, random says the following: we have some random arrangement of stones. there is 12 of them, right? So each one of them has 1 out of 12 chance of being selected. And if I want to select 3, that's how I would do it. Right? A simple random sample says I have 4 sets of 3 stones, and each one of them has a 1/4 chance of being selected. So that's the difference. Alright, so this is so far so good. Okay. So now how do we make it happen in real world? Because that's a lot more interesting. How do we construct operations and systems to be able to take those samples? So there's 4 common sampling techniques. There's 4 common sampling techniques. First one is convenience. Convenient sample is the use of the results that are easy to get. It's not random. You take a selfie, you post it on private on Facebook, and only your best friends look at me like, oh, girl, you're rocking, like, yeah, dude, you look awesome, right? You get this very straightforward, like very supportive thing. That's not a random sample, that's a convenient sample. It's not random, it doesn't tell you anything about what the population would think of your selfie, it just gives you a little emotional boost. Good for you. But it's not random. You want a random sample, post your selfie on Reddit with a little hashtag roast me and see how that goes. For people that have anxiety and less than superhuman tolerance, I wouldn't recommend it, because people are vicious on the internet. But that would be a more random sample, right? So again, convenient sample is not random, it's just use what's easy to get. Now let's talk about things that are actually random. Systematic. Systematic sample says the following. Take your things. I'm making so much noise. Well, take your things, put them in some kind of a line or order, right? Ta-da. And pick every kth member. So let's pick every third member. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. There, here's my random sample. Okay, that was too obvious. Fine. If this is too obvious, how about we going to pick randomly at, say, the 5th member, and then pick every third. 1, 2, 3, 4, 5, and then 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And there's my random sample. Right? So this is put population in some order and select every kth member, right? And if you want, you can start at some random place. I think that's a pretty cool way to do it. Okay. If you remember middle school and high school, this is how you got divided into random teams, right? Count of to 4, 1, 2, 3, 4, 1, 2, 3, 4, and all the ones go in one place, all the twos go in another place, and all the threes goes into another place, and that's how you got groups that were relatively random. Of course, if they announce that they're going to go for teams, you can stack yourself in such a way that you can do it. So there's some limitations to it, but it's relatively decent way to create a sample. All right, let's look at next one. Next one is called stratified. And stratified sample starts with breaking the population into subgroups based on some characteristic. Well, I suppose black and white is the characteristics we're gonna break these stones up. Right, satisfied. We could probably break them based on the weight or thickness or something, but let's do it this way. And then we sample each subset. Okay, I'm going to pick 2 out of here, and I'm going to pick randomly 2 out of here. And there's my sample. This sample has a benefit. The benefit of this sampling is what happens if this looks like let's create a couple of those samples, see how that goes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 20 of those, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 20 of those and 4 of those. Let's create another set. Population number 1. One, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. Population number 2. Let's make a third population. 4 and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so we have 3 populations. We're satisfied. There's 4 black and 20 white. Again, this is just randomly. All right, I'm gonna scramble them because it's 1 scrambled, 2 scrambled, right. So we have those 3 populations somewhat scrambled, right? All right, so we're gonna deal with this in just a second. So this is just prepared for this, and each subset, and then we're gonna go with cluster sample. So we had systematic, stratified, and cluster. Cluster sample says the following is divide population into clusters, right? Regardless of characteristic. And that's important, exclamation point. And then randomly um, randomly select a number of clusters, right, and sample all in a cluster. So you pick a cluster. Right, so we have a systematic, stratified, and cluster. So let's do systematic. Let's put them in. Let's attempt to put all those stones in a line. It's going to be a long line. Oh, it's going to be a very long line. All right, I think we managed. Right? All right, and then to be super fancy, where is this? Where is this? Dun, 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 dun. All right, and to be super fancy, we're gonna randomly pick our K. Randomly pick our K. We can go 2, 3, 4, 5, 6, 7, 9, 10. How many people? How many? There's 24 of them. 24. So say we want to sample 8. We're going to sample 8. All right. So this is completely random, right? I'm going to do my best attempt to shuffle it somehow. We're going to pick 2 cards. First card is going to be where do we start? Second card will be where do we sample? All right, ready? We're going to start on the third, 1, 2, 3, and then we're going to sample every 8th person. 1, 2, 3, 4, 5, 6, 7, 8. Right, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 3, 6, 8. And there's a sample. And there's our sample of 8. And that's the population. Population sample. Satisfied? I think so. It was well done systematic sample. All right, let's do stratified. Stratified means separate by some characteristic. There's 1. There's 2. And we want to pick a sample of 8, which means we have to pick a sample of 4 from each. So all 4 of those and some random collection of 4 of those. And there is a sample of 8. Right? And then cluster, I'm just going to separate them into groups of 4. So 4, 4, 4, 4, 4. Am I short? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. I'm short. Okay. So here's my 1, 2, 3, 4, 5, and 6 clusters. And again, we're going to do the systematic picking of clusters. So let's arrange them. Here's my clusters, and I'm gonna pick 2 clusters, and they're going to be, we're feeling lucky today, every third cluster. 1, 2, 3, check. 1, 2, 3, check. And we're gonna sample everybody in each one of those clusters. Hang on, wait. 4, 4, 4, 4, and 2. Okay, well. And there's my 8. Okay, so this is the 3 sampling techniques. And here comes the big one. Which one do you pick, or which one is better? Well, they all have some bonuses and some flaws. Systematic, if you're just looking at things that are relatively well mixed, with subgroups or sub-characteristics being relatively the same size, systematic is pretty good. Plus it's easy to do and it's relatively straightforward, right? Put people in a line and just ask them. And again, it seems relatively fair. There was 20 white ones, 1 black one, so you still got, 1 to 7, about the same proportion, right? That should be about right? For every 4 of those, there should be 1 of those, and just about should be 5. Well, this is about, the proportion wise looks about right. Little low on the black elements in this one, but at least there's some. We could have gotten none. There was a very low chance we would get more. And so this is good. Stratified, on the other hand, stratified gives the minority groups a voice, right? If we were picking just a sample of 6, then we would get 3 of those and 3 of those. So we got equal input, which is beneficial if you are in a population which has a very strong minority, as in a very small minority. Using stratified sample gives you a better input of what that minority might want to say, because there's less of them. In a systematic solution you won't get as many, right? So you get into this position where you actually have a better representation using a stratified sample. Of course, if you're separating white and black stones, in our case there's obviously a disproportionate power given to black stones because they will overrepresent in this. But if those white stones got divided into other groups, we would get a guarantee that all the groups are represented. Again, there is shortcomings from that method as well, but mind you, it allows for underrepresented population or aspects of the population, characteristics of the population, to be shown up. And then we get to cluster. Cluster is not bad. How do we divide people into clusters? We could do it by zip codes or phone numbers or some other number that doesn't exactly carry any implication on characteristics of male versus female, or Christian versus Muslim, or black versus white, right? The problem with that is that if you have a zip code that is predominantly black, right, and bunch of zip codes that are predominantly white, you run into the problem of choosing, purely white zip codes and skipping the black ones, right? If you take enough zip codes, one of those zip codes is going to be predominantly black, or predominantly Muslim or predominantly Catholic or whatever the other group is, right? But this runs into the problem that if you divide in zip codes, gerrymandering is one of the ways to ensure that all the black stones are in one group, and that this way that group won't be represented in many other. If you have a black stone in each one of those zip codes, right, and you have like only one or two, just whatever, one or two zip codes that are completely white, and you have to choose 3 zip codes, this is most likely going to look like this versus like that. So again, there is some benefit to doing cluster sampling, but cluster sampling is also susceptible to gentrification, to gerrymandering. So there's some limits on the usefulness of that, but it does provide for a random sample, right? Because we hope that the clusters are pre-mixed in such a way that that they are somewhat representative of the population. All right, so that's right. So that's the story behind the sampling techniques. Right, now we ought to talk about what do we talk about? Well, we can talk about the errors people make. So there's a non-sampling error and a sampling error. A sampling error, maybe differently. Let's try with the non-sampling error. Non-sampling error means just a math error. You added something somewhere wrong. You put things in the wrong table. You used the wrong formula. It's just very simple. You had the right data. You just screwed up the calculations. Okay, no, that's non-sampling. Sampling error is a little bit different, and the sampling error says the following: the sample characteristics, or characteristic if you were just checking one, is different than populations. In 2016, Hillary Clinton is supposed to win the presidential race against Donald Trump. She's supposed to. Every polling on the planet said that. Well, with exception, I think 1 or 2, but most of them said that she was going to win, and there was nothing nobody could do anything about it. She lost. And there's several reasons why she lost, and some of them are political. One of the reasons that the confidence was that high was there was a sampling error. What happened is the polling places didn't sample all the populations. They ignored, I believe, Latino and Latinx women, assuming that they won't vote, because in the previous elections they didn't vote, so they assumed that this election they won't vote either. And what they got, right, is a sample from a population which excluded couple subgroups. And because those subgroups got excluded, this gave a skewed view of what this whole thing looks like. Remember, we don't know what the population looks like. It's too big. So what we have is just a sample. If you have just this sample, right, nothing but this sample, the obvious conclusion will be that I took all those white stones from a big pile of all white stones. Maybe 1 or 2 black stones, but obviously I took a big enough sample, and there's no black stones here, which means that there shouldn't be any black stones here, and that's a problem because I never asked the black stones here, right? And so this is one of the big things. Is sampling errors are errors where the sample that you took has characteristics that are very different than the populations or different enough. All right, let's take a 5-minute breather, and then when we come back, I will get you started on a frequency distribution. All right, and we're. Oh, sorry, the fan is going. No. I suppose I am stuck in a fanless room. Otherwise, the mic picks up all of the air movement. All right, so where are we going with this? Frequency distributions. Frequency distributions. A frequency distribution is a list of values with corresponding frequencies. And frequency is exactly what it sounds like. It's just the number of times this showed up. All right. A frequency distribution. All right. So if we were to build a frequency distribution, we first needed some data. So let's say we collected some data on people that took Pubastats, right? So students and let's say we know that those people are between 18 and 40, say 45 years old. Maybe let's make it 44 years old. And the reason why I'm saying 44 is because a 60 is a new 40, right? Or a new 30, and a 70 is a new 40. So those people are young by spirit, right? They're in college, so we will count everybody who's older and somewhere in this group. I'm gonna ask them the age, and they're gonna be like, I'm 19. I'm like, you look at least 22, and they're like, yeah, I'm 72. I'm like, let's stick to 22 then. So we have this list of things. The problem with that is that if we created a list of frequencies for this, so starting at 18, ending at 44, what I might get is this kind of list of frequencies sticking out, and each one of those is a little bar chart and whatnot. 19 is here, 20, 21, and so on and so forth. It's nice. I'm very happy to have the raw data. The problem with raw data looking like this, it's hard to distinguish if there's any patterns. I mean, remember, we will be dealing with a lot of data. So having something that looks like this is somewhat troublesome. One of the other examples we can make about this, let's see if I can find it. Let's see. Pum, 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 pum. Alright, let's see if this works. So here I have an Excel spreadsheet with randomly generated human beings. I was bored at some point and I just generated a whole town. And we have their MasterCards, their MasterCard are these, their email addresses, the place of residence, gender, names, and so on and so forth. But I'm gonna focus here on age. I'm gonna focus on age, which is right here. And that's the age category. Now, first question you can ask me, how many people are there in this setup? Well, this specific set has 175,000 people in it, and that just seems like a lot. So what we would prefer to do is we would prefer to is to make some kind of a picture of it. Oh, the ages. And here comes the part. We would like to only 500 scores, okay. We would like to get something. If we get something that has this many classes, so this doesn't allow you. If we get something that has this many classes, we cannot discern the pattern. On the other hand, if we got something that looks like this, on the other hand, if we, instead of all those classes, we got something that looks like this, right? We run into the problem of not being able to do anything about it. Well, there's a lot more young people than old people, but that's about it. So we need to find some kind of medium between those. So if we go back to a very simple generator, this doesn't tell us anything, right? On the other hand, having raw data displayed doesn't tell us anything. On the other hand, if if I screw this up, on the other hand, this is much more manageable, right? Again, this is some random set of data I just pulled. This is much more manageable because now we have little sections and we can say, hey, there's a dip somewhere here, and then it goes back up and then back down. So what we want to learn how to do is we want to learn how to get somewhere between it's a comb and we cannot tell anything to it's two teeth and they are crooked kind of setup. We want to get somewhere between those two, and if we can do that, we can start building something that is actually meaningful, because right now our table looks like this, right? We have some value 18, 19, right, 20, and some frequency assigned to it, and this goes up to 44. and we have some raw data around it. This, we would prefer to put this into some 18 to something and then something to something else, and put it in couple categories that we can actually deal with. 2, 4, 6, 7, and 8. And then have some frequency assigned to those classes. Right? So a class is an entity that contains several pieces of data, values of data, right? And each class is the same size. So we need to talk about pieces of that. To talk about this, we need to talk about these two values, A and B. A is considered a lower class limit, and B is considered the upper class limit. Right? So a class is between A and B. Okay. So that's now we also have something we call class width. And class width is defined as the difference between two lower class limits. So in our case, that would be A minus 18 would be a class width, and that would be the same distance as this distance would be the same as this one, 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 and as this one. All of them would be the same width, right? That would be the class width. Now, class width could be also found out this way, right? Because if it's shifted on one side, it has to be shifted on the other. One way to make sense out of it is if you have a floor and a ceiling, right? There is some layers between the floor and the ceiling of the next floor. So when you measure the height of a floor, you have to measure this and not this, right? And that's how you get class width, floor to floor or ceiling to ceiling. All right, so we look at our data and we say, hey, I wanna have number of classes to be 8. Usually you're gonna be told in a question how many classes I want, or by your manager. If you have no information how many classes you need or you want to take, a good guess, or at least a beginning value, is to consider the number of objects in your data, in your frequency distribution, and then do this square root. So if you have 100 points, you should have about 10 classes. If you have 1,000 points, you should have probably around 100 classes to begin with. This will give you a lot of flexibility at the beginning to figure out how much. Hang on, there's some no. Sorry about that. People are making noise around the house. It's hard to focus. All right. So as I said, this will give you a good start on how many classes you should start with. Again, it's not a solid rule. Sometimes people want specifically 7 classes regardless of how much data you have. Sometimes less, sometimes more. So you have to kind of figure out where you are. Square root of square root of n is a good starting point. Excuse me, I'll be right back. Sorry about that. All right, so we want, in our case, we want to have 8 classes. So how do we do it? Well, we need to figure out class width. And to figure out class width, we take the maximum value of our dataset minus the minimum value of our dataset divided by the number of classes we want to have. Well, in our data set, we did say 18 to 44. So in our case, the class width equals to 44 minus 18. Seriously? Sorry. Divided by 8. Well, we do the math and that comes out to be 3.25. And here comes an important note. Mathematically, 3.25 as a class width is valid. It's valid, it's good, it works out the way we want it. It's actually spot on mathematically. The thing about social science is that this class width refers to age, right? This is age, and there is nobody above age 18 who classifies their age as 0.25. Which means that for a lot of people doing social science, 0.25 as age doesn't make sense. And if it doesn't make sense, they are very reluctant to use it. So if you look at it from the mathematical perspective, this makes perfect sense and you can use it and it works great. When you're looking at it from the social science perspective, especially when it comes to ages, people get a little twitchy about it. So they would prefer a class they can inherently comprehend. And so what we do in this case is we going to round this. And here comes the problem. If we round it down, we are risking that some of our values are not going to be included because we divided the big pie into pieces, and now we're going to use a slightly smaller piece to measure it, and that could be a problem. So can I create an example? Let's say this is all our values, and will this work? Yeah, this will work. So if this is all our values, and we pick a classes, we round down to a 3, right? And we run down into a problem where all our classes that we end up having are going to skip some actual value. Right? Those are classes. On the other hand, if we round up, our last class, right, might not pick up value, which means they will be half empty or even completely empty on the surface, right? So those are the two problems. Now, what does it look numerically? Numerically, it looks the following. If we round down, we have 18. The next one is 21, because the difference between two lower class limits is the class width, right? Round down means 3. 24, 27, 30, 33, 36. 1, 2, 3, 4, 5, 6, 7. 39. Well, this is 18 to 20, 20 to 23, 26, 29, 32, 35, 38, and 42. We ended up having 8, 1, 2, 3, 4, 5, 6, 7, 8, but we ended up at 42. What happens to 43 and 44? Why 43 and 44? Because that's the data we have. On the other hand, if we round up to 4, we get 18 to 22, 22 to 26, 30, 34, 38, 42, 1, 2, 3, 4, 5, 6, 7, and then 46. 21, 25, 29, 33, 37, 41, 45, and 49. If we round up, our last class is empty, because our data only goes up to 44, right? So there's a choice to be made. Are we keeping this, or are we rounding up? Because rounding down is just not good. I mean, there might be reasons why you want to discard the 43 and 44-year-olds out of your group, but mathematically that is a no-go, because you don't want to be losing data. Now, if there's a reason why you want to lose data, that's a different story, but that's a decision separate from the actual math part which we are talking about. So if you have a choice between this or rounding, in SPUBA and social sciences you're usually taught to round, and if you're rounding, you're not round down, you round up. All right, so that's that. So let's build this set of data. Let's build. So we have some class, right? And here in our case that's age, and we have 18 to 21, 22 to 25, 26 to 29, 30 to 33, 34 to 37, 38 to 41, 42 to 42 to 45, and 46 to 49. And then we have some frequency. Now, if you had the same raw data as I did, you would fill in the same way, but well, I just counted all the 18, 19, 20, and 21-year-olds in here, and I got 25 of them. I got 10 of those, 4, 2, 0, 4, 2, no, sorry, there's one of those, 0, one of those, and 0. That's the frequencies I got. How many people were in the sample? Well, if I sum all the frequencies, right, this Greek letter sigma means sum, means add all the frequencies. This is the frequency. So we add 25 plus 10 plus 4 plus 2 plus 1 plus 1. That comes out to be 43, right? And that's our size of our sample. So we're going to use n for sample size. So n means sample size, f is frequency, and that big letter right here, which right, this is sigma. It's a capital sigma, means sum, means just add things up. All right, so that's this. So we got this. Cool. The problem, well, again, remember who you're talking to. Your data isn't given most of the times to somebody who understands statistics. Your data is given to somebody usually who didn't make it in stats, and now they're trying to make decisions about the rest of the plan. So you have to give them something that they can understand. If I told you 10 out of 43, do you know how big 10 out of 43 is? 4 out of 43? 2 out of 43? No. But on the other hand, if I told you something is 10% off, you'll be like, yeah, well, that's easy. So what we have here is something called relative frequency. Relative frequency is a number that corresponds to the proportion this frequency is in the total number of frequencies around. So in this case, relative frequency is 25 divided by 43 times 100%. So in this case, it comes out to be 58.1. And then we can go 23.3, 9.3%, 4.7%, 2.3%, 0, 2.3, and 0. Couple notes about this. One note is that those percentages should add up to 100. They don't necessarily do. The reason why they don't do is because they're all rounded. How do we know it's rear-rounded? The difference between 1 and 2 is factor of 2. The difference between 2.3 and 4.7 is not. Means there was some extra digits here that got rounded, because this should be twice as big as this, and this should be twice as big as this, and they are not. So there is some information getting lost when you start doing relative frequencies and this. But relative frequency equals to the class frequency divided by sum of all the frequencies times 100%. That's how you calculate. All right, easy. All right, so what's next? Well, what can we do more? We could get cumulative frequencies. And cumulative frequencies is telling us how many items belong to beginning of the first class to the next one. So in this case, there's 25 of them. But in the cumulative frequency 18 to 25, well, there's 35 individuals in 18 to 25. 18 to 29, well, we add this plus this plus this, so that's 39. 18 to 33 is 41. 18 to 37 is 42. 41 is still 42. 18 to 45 is 43, and then 43. So cumulative frequency just adds all the previous frequencies together. And the reason why we do that is to show where the biggest change is. One of the biggest changes is here. There's 10 difference, and the smallest changes are here, or there's some no changes at all. So this is what this is used. And what? Well, we could graph it. So we could draw histograms. And I know you heard the term histogram before, but maybe you didn't hear this definition. Histograms are just bar charts with PDA. So those are touching bar charts. And there's a reason for it. If I were to graph this, frequencies and classes, there's 8 of them. So 1, 2, 3, 4, 5, 6, 7, 8. And this will be about 25. So this is about 10. This is about 4. This is about 2, this is about 1, that's 0, and this is about 1. If I graphed it here and I said, hey, this is 18 to 21, this is 22 to 25, and so on and so forth. That's 25, that's about 10, that's about 4, right? If I graphed this, and this actually happened to me, the first question when I presented this chart was, what happens here? Why didn't we include those people? Why didn't we include those people? What are those people? Those are supposedly the people that are not 21. They're older than 21 but younger than 22. Do you know anybody who's older than 21 but younger than 22? It's impossible, right? Because in a grand scheme of things, right, 18 to 21 and 22 to 25, there is nobody in this little section. There is nobody, because either you're 21 or 22. If you're 22, you're in this category. If you're 21, you're in this. There is no one 20 above 21, below 22. But the gap persists, and my boss was, well, he was special. So what I end up doing is I end up employing a histogram. And what a histogram is just a bar chart that got little expanded, right? We should make this line straight. Instead of lines right here, I just have lines right in the middle. And now, right, there is no question what's going on between. There's no question what's going on between, because there's nothing in between. You're in this category, you're in this category. How did I achieve this? Well, I achieved this by finding this point, and this is called the midpoint. And it's a point between 21 and 22. Well, so if you take 22 plus 21 divided by 2, you get 21.5. And so if I graph it, I'm graphing it, right? I have to expand it both sides. So I have to expand it here to 17.5 to 21.5, and then graph 21.5 to 25.5. And by graphing that, right, I avoid the stupid question, what's happening in the middle? Right, so we can add midpoint here, and that's, well, there's 2 of them here. There's 17.5, right, because the one on the left, and 21.5, and then we have 25.5, 29.5, 33.5, 37.5, 41.5, 45.5, and 49.5. Now, here comes the part where I lied a little bit. This midpoint is between those two, right? And this midpoint refers to a point between this class boundary and this class boundary, right? So what this becomes in reality doesn't become a midpoint as such, it becomes a class boundary, right? So this is not a midpoint per se, this is a class boundary, right? This is a new boundary between this class and this class. So, right, because if you were looking for a midpoint, you would probably want to find this right here, right? The midpoint for this class, right? So those are class boundaries. The class midpoint would be again the average between those two. So in our case 21 plus 18 divided by 2. But we're going to cover this later. Class boundaries are much more interesting here, right? So the midpoint between this and this in this blank space over here is called a class boundary, and that's this. And what it does is just extends the two things slightly wider, just so the visual perception is that they're touching. Yes, no, maybe. I'm assuming since nobody's talking to me, that's a yes. Let me double check. Yep, I'm still alone talking to myself. Alright, so how do we deal with class midpoints? Well, a midpoint will be exactly the middle of this. So midpoint would be 21 plus 18 divided by 2. And in our case, that would end up being 19 and a half. Right? So we have class boundaries and a midpoint. And then the next one will be 25 plus 22 divided by 2. So that will be 23 and a half. Or we can realize that right here, that's a class width. So the next one will be 27 and a half, 31 and a half, and so on and so forth. Right? So this is a lot of information. So far, any questions? All right. I think that's enough. We've been at it for it feels like for a while, for 2 hours. So I think that's enough for one big chunk, and then I will continue with describing data in the next video. Please take a look at the resources posted on the website and some of the social calculators which will help you do those calculations. They are not very difficult to operate, and as long as you understand the theory, you're more than welcome to use them. And on that note, thank you for joining me, myself, and I, and I hope to see you soon.